Wide area networks run long distances, and they connect different offices and buildings. Organizations typically do not own all the land upon which their WAN circuits run. Um, take take IBM for example. They have offices in California and in Florida. They don't own land space between California to Florida. There's a great deal of leased circuits involved with that. With a WAN may span a city, region, or even countries, and that's common with companies like General Motors, who have a large presence in China now. So, as we kind of just discussed, WANs are built using leased circuits from common carriers like AT&T, Sprint, Verizon. Comcast is definitely on that list. So that's the basic idea, that leased circuits are being used a lot with WANs. Thank you. Wide area networks involve common services. These services are dedicated circuit networks, packet switch networks, and virtual private networks. Thank you.
Hey, my name is Nuria Lopez, and thank you for viewing and participating in my presentation for circuit switching versus packet switching. Even though we've learned a bit on packet switching and circuit switching throughout this course, I actually wanted to get into more detail and show as to why I decided to use this topic. Many of us are familiar with telephones and computers and how technology has improved over the past few years. Now, this is what interested me. Most of us have used analog telephones before. You know, the wall type of telephones, instead of the current cell phones that 99.9% of us use and own. Yes, I grew up with this kind of phone. Ironically, they still exist. These kinds of phones use a circuit switching network. How does this work, you ask? Well, it's simple. I'll use an example. When you place a call to someone on an analog telephone, a dedicated connection is set up between the both of you. While this call is going on, only you two can use that telephone line. Once your call is finished, the connection is broken per se, and it becomes available now for someone else to use. Circuit switching is defined as a telecommunications technology by which two network nodes establish a dedicated communications channel, circuit, connecting them for the duration of the communication session before the nodes may communicate. This has been used for many years because it's something consistent, something steady, as a phone call between two people would be. With technology evolving, communication has definitely changed just in the past 15 years alone. Things needed to change. Faster connections, easier ways to send information. Years ago, 56K modems were introduced in order to connect to the internet. Thinking back, this was very frustrating because it was a slow connection. Now DSL and cable modems are coming in with faster speeds in order to download and upload files efficiently. Routers are used to do the dirty work. And this is where packet switching comes in. Using the same idea with the phone, just imagine it with the internet. It's not just one connection to another person as a phone would do. It's billions of computers all connected together in a big combo. But how can this be done, you ask? Packet switching. Packet switching is a method of breaking data files into small packets or chunks in order to send them across a network. A good example for packet switching is VoIP, Voice over IP, as it's called, or even Skype. The first experiment VoIP call was made in 1973, but the first software designed to provide users with internet calls didn't appear until 1995. A lot of things now are using VoIP, but I'll get into that later. It's not just a phone call anymore. It's packets being sent through a network, chunks at a time, so it makes it easier and not cluttered. So how does packet switching really work anyway? Well, each packet is sent with a header address, so it knows exactly where to go. Sometimes it may not be the shortest or best route, but it gets where it needs to go. The header address also shows the sequence for reassembly, so when they get to the destination computer, it's put in the right order. A packet also contains details of the number of packets that should be arriving to the other side, so if one packet fails, the other computer will get a message back asking for that packet to be resent. I'll use an old story to compare and contrast the difference between packet switching and circuit switching. The battle between circuit and packet technologies has been around a long time that it's starting to become like the old story of the tortoise and the hare. In this case, the hare is circuit switching, fast, reliable, and smart. The hare starts out fast and keeps a steady pace, while the tortoise starts slow but manages to double his speed every 100 meters. If the race is longer than 2 kilometers, 1.2 miles, the power of compounding favors the tortoise, packet switching. In a circuit switch world, when the phone line would go down, the call couldn't go through. But in a packet switch world, multiple routes can be established, so if a line does go down, a packet can switch to a different route in order to keep the line communication going. There are a bunch of advantages for packet switching above circuit switching. Just consider a few examples. This type of network is more secure. Bandwidth can be used to its full potential. Devices of different speeds can actually communicate with each other. It's not affected by line failure since it tries to redirect its signal. And no waiting. You don't have to wait for a direct connection to become available. And even during a disaster of some sort, when the public telephone network doesn't work or it goes down, emails and texts can still be sent. But as with everything, you do have your disadvantages. You may be able to use bandwidth to its full potential, but if there's a heavy use, it may cause a delay. Since working with more data and not a dedicated line, data packets may become lost or corrupted. I favor packet switching more than circuit switching. Technology is arising all the time and evolving into bigger and better things, and I know that eventually packet switching will become stronger and the future for data as we know it. I work at a distribution center for t-shirts, and I deal with the everyday hustle and bustle of picking orders, shipping, and receiving. A lot of this work is manual, and VoIP is becoming a part of our daily routine for warehouses like ours. There are companies out there that have invested in programs for voice picking, where an automated system is telling an associate where merchandise is stored within the warehouse. You don't have 10 pages for an order anymore. You have a machine telling you where to go. You go to that particular location in the warehouse, and voila, you have your order. You put the information together, tag it, wrap it, and wait for the customer to pick it up. It's simple as that. And it's something that is getting bigger and bigger and more every year, every day, every month. On another level, when we have conference calls with corporate members, we can use programs like Skype to create video conferencing. We have been in conference calls with private label vendors that are in China, and we can speak to them and see them like if they were right next to us. For gamers, you have programs like TeamSpeak or Ventrilo, where you can communicate with people around the world to play games like World of Warcraft, Call of Duty, etc. Technology is moving things in the direction of VoIP, and it may not be long before the internet phone and the cell phone are the remaining 2 primary methods for voice communication. Eventually, we'll be seeing Star Wars in the future of packet switching and phone calls.
That was an excellent presentation. I'd like to point out this is the URL if you wanted to see it. It's Nuri Lopez. It's a little bit old, but the information is still very relevant. I also wanted to clarify, she mentions circuit switching all the time throughout this video. You can use dedicated circuit and circuit switching terms interchangeably. So when she's referring to circuit switching, that is the dedicated circuit that my slides describe. Now let's go into dedicated circuit networks, or also circuit switching networks if you prefer to call them that. I'll accept either. Dedicated circuit networks use full duplex circuits from common carriers called leased lines or private lines to create point-to-point links between organizational locations. The carrier installs the circuits that connects the locations. You connect LANs to leased lines using modems, multiplexers, or CSU-DSU devices, or or channel service unit, data service unit. You have a MUX, which we discussed in Chapter 3, or multiplexer. That divides high-speed circuits into several slower logical circuits, such as the T1, the T2s, the T3s, what have you. Dedicated circuits are billed at a flat rate per month with unlimited use of the circuit. Adding and removing lines or increasing or decreasing capacity may be difficult, time-consuming, and expensive because it usually involves bringing in the carrier to install the new upgraded circuits. So there's usually a lot of cost and expense involved in upgrades. Thank you. The three architectures for dedicated circuits that we're going to focus on are the ring architecture, the star architecture, and the mesh architecture. We're also going to discuss the fully connected architecture, also known as the full mesh architecture. So we'll see examples of that as we proceed. Thank you. This picture below shows us the ring-based design, or the ring architecture. So, for example, let's say you need to send some information to New York and you're in Vancouver. You could send that message and it would go to Toronto and then to New York. So it would have one hop there. However, let's say there's a traffic problem and there's something wrong with the network. Then what's the only route it's got to get to New York? It would have to go through San Francisco, Los Angeles, Dallas, Atlanta, and then finally to New York. So there are some limitations with the ring-based architecture. It's very simple, but it's also somewhat limited as far as its features and its functionality. Thanks. Here we see an example of the star-based architecture. This star in this architecture is centered through Toronto, which is great. Again, if I'm in Vancouver, I need to send a message to New York, it has one hop through Toronto. If I'm in Dallas, I'll have one hop through Toronto to get to New York. So from that perspective, there's very few hops, and the star design can quickly deliver a message compared with the ring design in some instances. However, let's imagine what would happen if Toronto goes out. You'd lose the complete entire network. Thanks. Here we have a couple examples of the mesh design, and there is really no rhyme or reason to this. There's a lot more routing involved in a mesh design. Therefore, there's a lot more cost and expense, and there's a lot more setup involved. So really, the ring design is the least expensive, and the mesh design is the most expensive architecture. And that also kind of goes along with the level of complexity associated with that particular architecture. Thank you. And we also see here the full mesh as well as a partial mesh design. Thank you. In the previous slides, I discussed briefly some of the advantages and disadvantages associated with each type of dedicated circuit architecture here. Please take a moment, look this chart over, and make sure you understand the advantages and disadvantages, and also why these are disadvantages or advantages. Thank you. Now we'll discuss the two different types of dedicated circuit services. There's the T-carrier network and the SONET, or synchronous optical network. Thank you. Now we'll discuss T-carrier services. They're the most commonly dedicated circuit used in North America because they've used copper wires, and a lot of that is in place. It's very similar to E-carrier services used in Europe. If you look at the T-carrier designations, there's the T1 through T4, as well as the fractional T1, or or a portion of the T1. So a T1 can be subdivided into 24 different fractions. So that's how the speed is broken down. When I was working at the bank, we were putting in a couple different T1s. That's how we decided to manage the traffic that seemed adequate for our needs. The T-carrier services are greatly improved since then. But kind of look at this, get an idea of how the chart is set up. Thank you. Now let's discuss synchronous optical networks or SONET-based networks, which are fiber. And the standard that SONET uses is ANSI, which is from the American National Standards Institute. So, does your standard? It's similar to the SDH, or the Synchronous Digital Hierarchy, used outside of North America. North America does things different than they do in other countries, such as countries in the EU and what have you. They're going to use fiber there too, but it goes by a different standard, and there are some differences. So please look at the chart below, and it will go into some detail. Thanks. Now we'll discuss packet switch networks, which operate more like LANs and backbone networks than dedicated circuit networks do. So the WAN almost behaves as if it's all part of one LAN. Obviously, if you were to look into the way the packets are being sent and look at the routing, you'd see that that wasn't the case. But the connection to the carrier network is made using packet assembler disassembler protocols. So that's the PAD. And it translates messages between their different protocols, and the frame relay assembler disassembler is an example of that. Typically, the customers pay a fixed price for a connection to the carrier and then a fee for the data transmitted. So think of this as like a Verizon type network. Thank you. In packet switch networks, packets from separate messages may be interleaved to maximize efficiency. In other words, they might be packaged up together. Permanent virtual circuits, or PVCs, are connections between different locations in the packet network. They make packet switch networks act or seem to be dedicated, even though they aren't, and it's set up using a virtual circuit. Switched virtual circuits, or SVCs, change dynamically. So that's the differences. Thank you. Data rates are really important to consider when working with packet switch networks. Different locations may have different transmission speeds to the carrier network. So that's very common, depending on whether you're tied into a level 3 network, a level 2 network, or a level 1 network, which we'll go into very, very shortly here in the next chapter. There's also the CIR, which is the committed information rate, which is the rate of data transfers provided by the ISP. So you have to keep up with them and make sure that they're being honest. Packets exceeding the CIR up to the maximum allowable rate may be discarded if the network becomes overloaded. So if you're sending too many packets and you have been sending them and the network is slow and they're able to go through, great. If not, there's no guarantee that packets exceeding the maximum allowable rate will not be discarded. Thanks. There are many different types of packet switch services. The most common and the ones that we're going to discuss are frame relay, Ethernet, and MPLS. Thank you. The frame relay includes a flexible Layer 2 standard for encapsulating and packet switching in wide area networks. It's still common, but its usage is declining, and it was designed for high performance and efficiency, but it's lacking in error control and it's unreliable. So for that reason, it's still around, but it's going to go away. Thank you. So Ethernet is really taking over. When converting to and from backbone networks and LAN protocols to WAN protocols, it does slow communication, and many carriers are starting to switch over to Ethernet for their WAN services. These new packet services bypass the public switch telephone networks. Like I said, when I had RRT1 put in at the bank I worked at, we went through Ameritech. That was the telephone network. Ethernet is also becoming less expensive because of all the availability of resources, both physical and human resources alternatives out there. So Ethernet's really taken over. Thank you. Multi-protocol label switching, or MPLS, can be used with a variety of Layer 2 protocols, so switching protocols. Label is applied when entering the carrier network between Layer 2 and Layer 3's headers. So MPLS, for that reason, is sometimes referred to as the Layer 2.5 protocol. Label is used in forwarding decisions and traffic engineering. And packets can be switched using labels faster than a complete IP address and routing tables. So it can be a fast packet switch network if it's using MPLS. And thank you. Okay, as you know, the trend that we're all facing and seeing nowadays is the trend and the movement towards everything being IP services. 10 years ago, we still had POTS lines or public switch telephone networks out there. And now you're seeing a lot more bundled packages, and your telephone services are being delivered through IP networks. And Ethernet and MPLS are the most commonly used in these IP networks. And that seems to be the direction that technology is moving or has moved towards. Thank you. Now we'll discuss VPN networks. Many of you may be familiar with VPN networks from your job. I know I certainly am. And I know where I've worked jobs where we haven't had VPN networks. So VPN networks provide equivalents of private packet switch network, but over a public internet. It creates a virtual circuit, often called a tunnel, and that may use dedicated hardware such as a VPN firewall or a VPN gateway, or be interrupted in software. VPNs can be implemented at Layer 2 or Layer 3. Thank you. This is a diagram of how your typical virtual private network or VPN is set up. You have a backbone network which would be tied into your VPN gateway, which then connects to a VPN tunnel, which we're going to go into more information on. And that would be received by another VPN gateway at a different office location. Thank you. Now we're going to go over the different types of VPNs. There's the intranet VPN, which provides virtual circuits between organizational locations over the internet. So we might have an intranet VPN set up between the Hartford campus, the West Hartford campus, and the New Haven campus with Albertus here. We don't, but we could. An extranet VPN is the same concept as an intranet VPN, except that different organizations over the internet are allowed to connect, such as customers and suppliers. Access VPNs are very common, and many of you have probably seen them in the past. They're the type of VPNs that enables employees to access an organization's network from remote locations over the internet. I connect to an Access VPN for my job every day. Like I said, I'm sure many of you do too. Thanks. Now we'll discuss the advantages and disadvantages associated with VPNs. The advantages are that they're very inexpensive. Usually a little bit of client software and a VPN gateway is all you need, so they're also very flexible. The disadvantages are they're not dedicated internet circuits, so internet traffic can be unpredictable, and there could be multiple incompatible implementations, and so not all vendor equipment and services are going to be compatible with each other. So VPNs are very useful, but they do have disadvantages. Thank you.
Please notice the URL that is right here. This is the user that published this information. It's very well done.
Hi, I'm Barry Williams. I've been a Networking Academy instructor since 1997 and presently serve as the educational chair of the Skills USA Internetworking Contest. You know, historically, businesses have had to rely on least dedicated circuits, T1, ISDN, OC3, and others to interconnect their offices. These leased circuits provided a reliable, private, secure method to share business communications. But they also have limitations. Leased circuits can be expensive and often rise in cost as the distance between offices increase. Also, workers were required to go to an office or to a branch office to access the business network resources. This video will give you an overview of the Virtual Private Network, or VPN. VPNs have become the logical solution for remote access, providing secure communications with access rights tailored to an individual user, enhancing productivity by extending the business and corporate networks and the applications. They increase flexibility and they also reduce the cost of communications. Anytime, anyplace network access gives employees great flexibility regarding when and where they perform their job functions. Using the VPN technology, employees can essentially take their office wherever they go, thus improving response times and enabling flexible work schedules. Let me offer you an analogy that maybe will help you visualize how a VPN is different from other network access. We all live in communities where the products we consume are delivered by many types of transport systems. So representing the internet and the interconnectivity of our homes and our businesses, let those be the roads and the highways upon which we travel. Representing the IP packets that travel on the roads are transport trucks. And these transport trucks carry data from one location to another. As you stand by the side of the road and watch these trucks go by, you're going to notice that some of these trucks are carrying their contents out in the open so that you can see what the truck is hauling. And you will also see other trucks that have enclosed trailers that protect their contents or hide their contents from the observers along the road. So where does the VPN fit into this analogy? The trucks that have open trailers are non-VPN carriers, and the trucks that have closed trailers are VPN carriers. A VPN truck provides a dependable and a fast means to keep us separated from other traffic and provide a secure means of transport. A VPN truck is easy to access. It's capable of picking up its packages in public locations like hotels and airports, as well as from our individual homes. We have the ability to grow our network in multiple ways. One of these methods is to add more leased lines. This method can be an expensive solution. By scaling our network with VPN technology, we can better utilize our existing data services and provide connectivity from more locations. In fact, scalability is the major advantage that VPNs have over leased lines. Virtual private networks rely on tunneling to create the private network that reaches across the internet. Essentially, tunneling is the process of placing an entire packet within another packet and sending it over the network. The protocol of the outer packet is understood by the network on both points. These points are called tunnel interfaces, and this is where the packets enter and exit the network. Tunneling requires three different protocols. The carrier protocol, the protocol used by the network that the information is traveling over. And then there's the encapsulating protocol, the protocol SSL, IPsec, or others, that is wrapped around the original data. And then the passenger protocol, the original data. Now this can be IPX, NetBEUI, or IPE as we normally see. Tunneling has important implications for VPNs. You can put a packet that uses a private, non-routable IP address inside a packet that uses a globally unique IP address to extend your private network over the internet. You can also place a packet that uses a protocol that is not supported on the internet, such as NetBEUI. And you can place that inside an IP packet and send it safely over the internet. As you can see, VPNs play an important role in scaling your network.
On this side, we go through the cost, reliability, and data rate comparisons between the different types of dedicated services and the packet switch services, as well as VPN services. So study this diagram and you'll get an understanding of the different types of design practices as they're associated with wide area networks. Thank you. When discussing improving WAN performance, considerations need to be made with devices, circuits, as well as network demand. So these three bullet points always need to be considered and monitored. Thank you.
And thank you. That concludes the chapter.